Okay. So the first sort of topic that I have prepared is linear combinations. So here I've written out the definition of linear combinations. So basically, if you have a set of vectors like v1, v2 through vk, a linear combination is just any expression like this, like c1 times v1 plus c2 times v2, etc. So it's basically like a sum of scalar multiples of vectors. That's what a linear combination is. And so to start with, I just have a couple of simple examples, just asking, is a given vector a linear combination of some other ones? So I'm just gonna work through these examples first. So I'll start with this one that I have prepared. So we're given the vector 4, -5. I want to check if it's a linear combination of the given vectors v1 and v2. So how you want to go about answering this question is, well, let's take the vector 4, -5. And I'm checking to see, is it equal to a combination of v1 and v2? So here on the left-hand side, I'm going to create a linear combination of v1 and v2 right now. Okay. And what I want to do is see if I can solve for a c1 and c2 that will satisfy this equation. Okay. Okay. So whenever you're doing this type of question, this will basically lead you to a system of equations. Okay. Okay, so here, this vector equation, I could rewrite it. If I focus on the components, you have like 1c1 plus 2c2 must be equal to 4. And then you have like 1c1 plus 3c2. Then that must be equal to -5. So we'll try to solve for c1 and c2. And how you solve for c1, c2, it really doesn't matter. Here, I think the simplest thing I could do is maybe if I just subtract equation 2 from equation 1, the c1s will cancel when I subtract. We'll also have 2c2 minus 3c2, so that's negative c2. And on the other side, we will get 4 minus a -5. So it's actually 4 plus 5. So I get c2 to be -9. Okay. And then now that I've solved for c2, I can plug it back into either of these equations in order to solve for c1. So if I take the first equation, c1 plus 2 times c2, that must be equal to 4. So solving for c1, it looks like c1 is going to be 4 plus 18, so it looks like c1 will be 22. Okay. So therefore, what this work shows us is that if we take 22 times v1, and if we add to that -9 times v2, that should be equal to vector b. And so therefore, b is a linear combination of vectors v1 and v2, because it is a sum of scalar multiples of the two vectors. Okay. Any questions about that? All right. So in that case, we'll take a look at the other question that I have. So it's the same type of question. But this time we're kind of moving up a dimension, so all of our vectors have 3 components. What am I doing? Okay. Okay, so let's see how we would work through this problem next. So I'll set it up in a similar way. We have this vector b that's given. And I'm checking to see if it is a linear combination of v1, v2, and v3. So I set up the problem the same way. I form a linear combination of v1, v2, v3. I set it equal to b, and again, I want to see if we can find a solution for c1, c2, and c3. Okay. So in this case, that leads us to a 3x3 system of equations. So if you focus on each of the components, you have 1 C1 plus 2 C2 plus 3 C3 equal to 2. Okay. Next, we'll have 0 C1 plus 1 C2 plus 2 C3 equals 1. And if you look at the last entry of everything, we have like negative C1 plus 0 C2 plus 1 C3, and that must be equal to negative 1. Okay. So to solve a 3x3 system like this, again, you can kind of do it however you want, but I think for a 3x3 system, it's probably easiest to solve it by doing elimination, especially now that you guys have learned how to do that. So what you could do here is set up the augmented matrix for this system of equations. Okay. So here I have the coefficients on the left-hand side, and then I'm going to augment it with what we have on the right-hand side. Okay, and then when we're doing elimination, and we'll definitely talk a little bit more later in the review about elimination, but when you're doing elimination, you do want to do it like one column at a time. So starting with the first column here, you want to get zeros beneath your first pivot. So I already have a 0 in the second row, but I want to make this -1 a 0 as well. So to do that, I could take row 3 and add row 1 to row 3. So I'm going to copy down rows 1 and 2 first. And then I'm adding row 1 to row 3. So that will give us another 0, 2, 4, and +1. Okay. And usually when you're doing elimination, your goal is to reduce to like an upper triangular form. So the next thing I'd be trying to do is get a 0 in this entry beneath like that sort of main diagonal. So to turn this 2 into a 0, some of you might think to do row 3 minus row 1, because 2 minus 2 would give you a 0, but that is no good. So let me kind of highlight why you don't want to do that. So if you did do like row 3 minus row 1, you would get a 0 in the third row here as we wanted. But notice you would also have to do 0 minus 1. So you would have lost this 0 that you created earlier. if you were to do row 3 minus row 1. So when you move to the second column, you have to use this second entry now in the second row as your next pivot. Okay. So instead of doing row 3 minus row 1, I have to use this 1 as a pivot to eliminate the 2 that's underneath it. So I'd maybe do like a row 3 minus 2 times row 2 instead. Okay. So when we use row 2 to eliminate row 3 here, here you will get 0 minus 0. So in other words, doing this operation does not undo that 0, so that's why we want to do it this way. Then you'll get 2 minus 2, so the other 0 that you want. Now here we're also going to get 4 minus 4, which is 0. And then we'd also get 1 minus 2, which is negative 1. So we've kind of produced this upper triangular form, which is usually what you want to do when you're doing elimination. At this point, what do you guys maybe notice in the matrix that we have at the end there? Okay, so let's see what we have at this last matrix. Okay. So remember that each row of these augmented matrices, each row corresponds to an equation. So if you look at this very last row that we got in this reduced matrix, this last row reads as like 0, C1, plus 0, C2, plus 0, C3 equals negative 1. And yeah, so that's correct. There's definitely no solution to this equation then. So that there would be no solution to our system of equations. Okay. All right, so then because we have no solution, going back to the original question, so is B a linear combination of V1, V2, and V3? Since there was no solution to this equation here, the conclusion would be that B is not a linear combination of the 3 vectors. Okay. So any questions about that example? Okay, all right. So let me see here. So I think I'll move on to kind of the next section. This span. Okay. So next I wanted to talk about span. And I'm not sure if you guys were using the word span, but you had some questions about span from like your first homework assignment, I think. So I thought I would introduce the word anyways. You'll definitely see the word span in the coming weeks during your class as well. So here's the definition. So the span of a collection of vectors is the set of all linear combinations of those vectors. Okay. And here I have a picture of 2 vectors u and v drawn. And I wanted to use this picture that we have. Oops. to kind of illustrate like what span is, like kind of visually. Okay. So I have two vectors u and v. So what I'm going to do in this picture is I'm just going to draw a couple of different linear combinations real quick. I'll try not to take too long doing this. I want to use some different colors. Let's maybe use this one first. Okay, so say for instance, I have u and v, and let's say I want to draw like the vector like u plus 2v in the picture. Okay, so to draw u plus 2v, what I'd want to do is I'd want to multiply v by 2, which would result in like doubling its length. So let's say that's about double the length of v. Okay, so then like this vector here, that would be 2v. All right, and then you guys may remember that when you have two vectors connected tail to tail, that their sum was like the diagonal of the parallelogram that they would form. So if I create like a parallelogram using the vectors u and 2v, and this vector here, that would be what this linear combination u plus 2v looks like. Okay. All right. And maybe I'll do one or two more of these, we'll see. But I want to do at least one more for sure. Let's maybe use green. So let's say I'm just going to draw another linear combination. Maybe I'll do something different. Let's do like negative u and then minus 3b. Let's try that real quick. So if I wanted to draw this linear combination, I would now have to like reverse u to get the vector minus u. So that'll be like kind of here. And then for minus 3b, so again, the negative will reverse the direction. And then we also need to triple the length to get minus 3b. That's maybe the 1, 2, 3, roughly speaking. So let's say that's maybe negative 3b. And then when I add the vectors minus u plus minus 3b, so again, that linear combination would be the diagonal of this parallelogram. Okay. So this is kind of what minus u minus 3b looks like. Okay. So maybe I'll stop there, but if I were to continue drawing like different linear combinations, it would continue giving me like different vectors. Okay. And all of these vectors that we're getting, all of these vectors lie within like the plane formed by the vectors u and v. And then kind of like vice versa, if you were to like pick any point in the plane determined by u and v. So let's just say if I pick a point like right out here, this vector could be expressed as some linear combination of u and v. So say if I were to multiply u by a scalar c, that brings me out to here. And then let's say I were to multiply vector v by a scalar, that would bring me like up to this point. So let's say that's maybe like dv for some scalar d. Then this vector here that I drew, this would be like cu plus dv. Because again, the sum being like the diagonal of this parallelogram. Okay. So like if you consider the set of all of like the points in this plane, all of those points can be represented as a linear combination of the two vectors u and v. So then kind of my point in this illustration is that the span of these two vectors so span, again, referring to the set of all linear combinations of them. Okay, would end up forming basically the entire plane that the two vectors u and v lie in. Okay. So that's kind of like a visual, I guess, of like what span is. So when you have two vectors u and v, as in this picture, the span of the two vectors just refers to, like geometrically, it just refers to the plane that they form. Okay. All right. So will the span of two vectors always be a plane? What do you guys think? Right, okay. So here it's important that your two vectors are not collinear so that they would form a plane. But as an example then, if you had a picture like this where the two vectors were collinear, so let's say that's u, and maybe like this is v. In this case, the span of the two vectors rather than being a plane, it would just be the line that the two vectors end up forming instead. So it's like this whole like infinite line that they lie on, that would be the span. All right, good. So then with that kind of in mind, I wanted to look at a couple of questions about span. These are kind of similar to some questions that you had. I think it was in your first assignment, it might have been your second one. Okay. But what we have here is a set of three vectors in R3. Okay. And the question is asking us to describe what the span of the three vectors is. So is the span of the three vectors a line in R3, or maybe it's a plane in R3, or maybe it is all of R3. Okay. So just looking at part A, I think this one is pretty simple. So when you guys look at these three vectors, what do you think their span would be? Right, okay. So yeah, in this case, the span of the three vectors would be a line. So what's the reasoning for that? When you look at each of the vectors, you'll notice that each of them happen to be a scalar multiple of the other one. So in particular, like V2, you'll notice V2 happens to be what, -2 of V1, right? Or -2 times V1. Likewise, V3 happens to be 3 times the vector V1. Okay. So the picture would look maybe something like this. So this is V1. V2 goes in this direction, should be double the length. And then V3 should be triple the length, but in the same direction. So V3 will kind of be like this maybe. we pretend that's triple the length. So yeah, in that case, you can clearly see since the vectors are like scalar multiples of each other, they all lie on the same line, and then that line that they lie on would be the span of the three vectors, okay? All right, good. Okay. So then part B is maybe a little bit more difficult. So looking at part B, I guess the first thing that's worth noting is that the three vectors definitely span more than just a line. Reason being because we can clearly see that these vectors are not like scalar multiples of each other, the way that they were in part A. So that means the span of these three vectors is going to be a plane or all of R3. Okay. So we need to kind of figure out which of these two would be the correct answer. And there's a couple of different ways that you can approach this problem actually. But I figured out maybe approach it the way that I think you were expected to approach it, at least on the first assignment. Okay. So here's kind of the idea. So when we look at the first two vectors, v1 and v2, we already know that v1 and v2 are going to span a plane because they are not scalar multiples of each other. So then what we want to do here is check whether the third vector v3, you want to check if v3 belongs in the plane formed by v1 and v2. Okay. So if that's the case, if v3 lies in the plane spanned by the first two, then in that case, since all three of your vectors are like coplanar in that case, that means the three of them would only span that plane that they all lie within. Okay. But then on the other hand, if v3 does not lie in the plane spanned by v1 and v2, then you would know that v3 kind of like sticks out of the plane and kind of forms like a third dimension. So they would end up spanning all of R3 instead. Okay. So that's at least like one strategy for how you could approach this problem. Okay. So then how to check if V3 lies in the plane spanned by V1 and V2. Well, remember that the plane spanned by two vectors like this, like sort of algebraically, it's the set of all linear combinations of those two vectors. So checking to see whether V3 lies in the plane spanned by V1 and V2, that's going to be equivalent to checking if V3 is a linear combination of V1 and V2. Okay. So what I'm going to do is kind of do what we did in the previous examples, where I'm going to form a linear combination of vectors V1 and V2. I'm going to set that equal to V3 because I'm trying to check is V3 a linear combination of V1 and V2? Does V3 lie in the plane spanned by V1 and V2? Okay, so here that if we just write out like the corresponding system of equations, so here we have like a 1c1 plus 0c2 must be equal to 3. Next we have like 2c1 plus c2 must be equal to 2. And then the last equation is negative c1 plus 1c2 equals negative 5. So in this case, we already have that c1 would have to be equal to 3. So let me take these two equations and plug in c1 equals 3 and see what that gives us. So in the second equation, 2 times 3 plus c2 would have to be equal to 2. And in this case, negative c1 and then plus c2 is negative 5. Okay. So if I solve for c2 in the second equation, 2 minus 6 will give me negative 4. But if I check the third equation, so adding 3 to the other side, this will give me c2 is negative 5 plus 3 is negative 2. Okay. Okay, so what does this mean? So this means that there's no value of c2 that would simultaneously satisfy both of these equations, because you see each of them gives you a different value of c2. Okay. So therefore, there's no solution c1, c2 to this system of equations. So what's the takeaway from that if there's no solution to this system of equations? So that would mean that V3 is not a linear combination of V1, V2. Meaning that V3 is not in the plane spanned by V1 and V2. Okay. And if it's not in the plane spanned by V1 and V2, then that would mean that the three vectors together must be spanning more than just a plane. So therefore, you can conclude they would be spanning all of R3. Okay. Okay. So then I'll just pause again and ask if there are any questions. Okay. So in that case, let's see here. I think that's all I had in that for now. So I guess the last thing I decided, or the next thing I decided to, that I would go over is linear independence. Okay. Okay, so linear independence, there's a couple of different definitions of linear independence. So I've written a couple of different definitions here right now. So I'll talk about each of them. So here's kind of like the first definition of linear independence and linear dependence. So let's take a look at definition 1. So here I have that vectors like v1 through vk. These guys are linearly independent. If none of these vectors is a linear combination of the others, okay? So then kind of like the opposite notion would be that these vectors are linearly dependent if at least one of these vectors is a linear combination of the others, okay? Okay, so before I look at definition number 2, let me kind of revisit some of the examples that we saw real quick just now. Let's go with this real quick, okay. Okay, so looking at like these two examples real quick. So these vectors v1, v2, and v3, they were all scalar multiples of each other like this. Okay. So here you can say that like v3 is a linear combination of v1, same for v2. So then these three vectors, they would be linearly dependent, since at least one of these vectors is a linear combination of the other ones. So again, like v3 being a linear combination of v1, for instance, okay? As for this example with these three vectors, if we were to ask maybe like, are these three vectors linearly independent or are they linearly dependent? So we saw in the end that these three vectors end up spanning all of R3. Okay. So because they end up spanning all of R3, I guess the idea is that none of them are going to be linear combinations of the other ones then. So like we kind of checked here that V3 is not a linear combination of V1 and V2. I didn't check the other possibilities, but for instance, like V1 could not be a linear combination of V2 and V3. Otherwise, they would be coplanar, and that would contradict that they span all of R3. So here in this example, none of these vectors are linear combinations of the others. So this would be an example where the vectors are linearly independent. So none of these vectors are a linear combination of the other ones. Otherwise, they'd be coplanar and only span a plane, and we saw that that's not the case. All right. So that's kind of like the definition 1 of linear independence. However, it is a little bit difficult to use definition 1 to check if vectors are linearly independent. So there's another definition of linear independence. So I wrote down the second definition here, definition 2. Okay. So definition 2 says that these vectors v1 through vk are linearly independent if the only solution to this equation here is the solution where all of the coefficients, so c1 through ck, if all of them are equal to 0. Okay. And then otherwise, if this is not the only solution, then the vectors would be linearly dependent instead, okay? So this, if you're like given a question like this, just given some vectors and asked are they linearly independent, for questions like this, it's going to be easier to use this version of the definition of linear independence in order to answer it. So I'm going to kind of illustrate with this example how to use definition 2 to go about solving this. Real quickly, I will note, so these definitions, they look different, but the definitions are equivalent to each other, meaning like if a set of vectors is linearly independent according to definition 1, it will also be linearly independent according to definition 2, and then vice versa, okay? Okay, so let's see how to use like definition 2, that specific formulation of the definition to solve this example. So what I'm going to do then is I need to look at this equation, C1V1 plus C2V2 plus C3V3 and equal to 0 on the right-hand side. So what I need to do is I need to try to solve for C1, C2, and C3 in this equation. And depending on what the solution or solutions look like, that will determine if they were independent or not. So let's just go about solving this system of equations here. So again, this is like a linear system of equations. And to solve a 3x3 linear system of equations, I think it's a good idea to just do elimination. So I set up an augmented matrix for the system. Okay. And then start doing like the usual row operations, trying to get it into that upper triangular form. Okay, so in this case, in the first column, we already have a 0 here. I want to turn this 2 into a 0 as well. To do that, I could take row 3 and subtract 2 of row 1. Okay. So let's see here, copy down row 2, and then this is now a 0. And then doing row 3 minus 2 of row 1. 3 minus 2 is 1. This would be 4 minus 4 is 0. And then, well, I guess on the right-hand side, it's always 0. So 0 minus 0 will be 0. Okay. And I guess we could probably stop here, honestly speaking, but maybe just to be formal, if you really want to reduce to the upper triangular form, what you could do here to make it upper triangular is actually, I guess you could just swap row 2 and 3. It's not really necessary though, but if you just kind of want to be formal, you could do this, swapping row 2 and 3. Well, actually, wait. That was kind of silly of me. That's not upper triangular. For some reason, I thought this would be a 0 when I swapped, but that's not the case. So let's not do that. Not that it hurt, not that that's not allowed, but so if I really wanted to reduce to upper triangular, I guess I could do row 3 minus row 2 instead, rather. So let me just do that real quick. Okay. So then let's see here. You get that for row 1. I'm not changing row 2 either. And then when I do row 3 minus row 2, so again, this remains a 0 when you use this as your next pivot. Now we get 1 minus 1, so we got the other 0 we want. 0 minus -1 is +1, and then you still have 0 on this side. Okay. So now we have like that upper triangular form that you usually go for when you're doing elimination. So let me see what's going on with this. If we were to like convert this back into a system of equations, This last row gives us the equation 0C1 plus 0C2 plus 1C3 equal to 0. Here you'll get like C2 minus C3 equal to 0 again, and then you have like C1 plus C2 plus 2C3 is 0. So normally after reducing to the upper triangular form, you do your back substitution. But here it's pretty clear if C3 is 0, plug that in, C2 is 0, plug in C2 and C3 are 0. And here you can pretty clearly see that the only solution that we have is that all the C's are equal to 0, okay? So according to this definition here, since that was the only solution that we found to this equation, therefore the conclusion is that our three vectors are in fact linearly independent, okay? All right. So any questions about that right now? Okay. Then just kind of like a small comment on this example as well before I continue. So if you're just trying to solve a system of equations, you don't necessarily have to reduce all the way to the upper triangular form like I did here. So I just want you guys to be aware that, it's somewhat flexible on what you do when you're just solving a system of equations. So for instance, here you could have just stopped at this point and converted this into a system of equations. Because this last row is already pretty convenient. It already gives you C2 is 0. So then therefore you can see C3 must be 0 then. And then if C2 and C3 are 0, again, C1 will have to be 0 as well. So you don't necessarily have to go all the way to this step, but maybe if you're like not sure, then it never hurts to go all the way to the upper triangular form, okay? But if you see something like this and you notice, oh, hey, that's pretty convenient, you can go ahead and stop there and just solve doing the back substitution again, okay? Yeah, yep, so to see if vectors are linearly independent, it does boil down to solving a system of equations. And that was the same for questions involving span and linear combinations, okay? All right. Now, before I go on, I'd like to do another like linear independence example similar to this one, but this time I would like to alter the example slightly just to kind of show you basically what would it look like if the vectors were actually linearly dependent, because you probably want to kind of be aware of both scenarios. So if I remember correctly, this 3 that I wrote down was telling me that if I change this 4 to a 3, then the vectors would be linearly dependent, but let's check. Okay. Sorry, are they linearly like independent? I mean, I guess, or not. It's the same question, I suppose, but. Okay, so I'm going to, approach this example the same way that I did this one. So we have this equation that we're trying to solve. I ended up setting up this augmented matrix, so I'll do that for this one as well. Okay. It's not necessarily necessary that you like write this out and then go to the augmented matrix. I would say it's perfectly okay to go straight from this question straight to the augmented matrix, okay? So maybe like if you want to save a little bit of time and regarding how much you're writing, just jump straight to that. That should be fine. Okay. So if I were to try and do elimination again on this example, so let's say I do like row 3 minus 2 row 1 again. So then that gets us the 0 that we wanted there. 3 minus 2 will give me 1. This would be 3 minus 4 is negative 1. Here you get 0 like that. So if you were to continue one more time trying to get to the upper triangular form, so you'd want to eliminate this 1 next. So we could do that by doing like row 3 minus row 2. But you can see in this example that rows 3 and 2 are identical. So if you do row 3 minus row 2, it gets us this situation. Where we kind of have like this like row of zeros at the very bottom. So maybe I'll pause for a moment and just ask you guys like, what's happening when we get to this point? Like, what is that telling us regarding like this system of equations that we were trying to solve? Okay. So what's going on here is this is an example of where you actually have infinitely many solutions to the system of equations. So it's kind of going to talk about it later, but I'm sure you guys are kind of familiar, like for a system of equations, you've kind of learned that there's like 3 possibilities, right? So a linear system of equations could have a unique solution, could also have no solution, and if it's neither of those two, then it's instead going to have infinitely many solutions. So those are like the 3 different possibilities. So this is actually an instance where you have infinitely many solutions, okay? So you guys haven't really done too much, with the situation where you have infinitely many solutions. It's really like so I guess like after the first exam, that's kind of when this class usually delves more into the situation where you have infinitely many solutions. Okay. I guess for now, I don't know how important it is to kind of like write out the solutions. For this problem, it's not too important. So if you can identify that there are infinitely many solutions, you can make the conclusion that the vectors will be linearly dependent. So why is that? So if you go back to the definition that I had up here real quick. So the vectors will be linearly independent if this was the only solution, to this equation, so that C1, etc. are all 0. So this is not the only solution. Essentially, you have more than one solution, so you have infinitely many solutions. So in that case, the vectors would be linearly dependent, okay? So I'll talk a little bit more later in my review about like what's maybe how to know that you have infinitely many solutions. And then I don't know if you really need it for the first exam, but I might touch on like how to handle that situation if you wanted to actually like write out the solutions when you have infinitely many of them. But for now, I just wanted to highlight when you're checking for linear independence, if you have infinitely many solutions, when you solve this system of equations, they are linearly dependent, okay? Okay. I think I will go ahead and move on to the next topic, which is dot product and kind of related notions. Okay. So here I wrote down a couple of definitions or formulas. So the dot product of two vectors, you remember you multiply their components together and then you add all of that up. Here, this is like the norm or the magnitude or the length of the vector u. People call it like different things. So norm or magnitude or length of u. Okay. And I wrote down two formulas for the norm. So on the one hand, it's the square root of the dot product of u with itself. But kind of explicitly, like u dot product with itself would be u1 squared plus u2 squared all the way, etc. Okay, so then that's the formula for the norm or the length of a vector. There is also this formula involving dot product and the angle between the two vectors. Okay. And I just wanted to like very quickly do some of the computations of these quantities using these two vectors as illustration. I'd like to think most of you know how to do this, so I'm just going to do it pretty quickly, okay? So if we want to do like u dot v, okay, so according to this formula here, we would do 2 times -4 plus -1 times 0 plus 3 times 1. So that would be -8 plus 3 is -5, okay? If you wanted to calculate like the norm of, say, vector u, okay? So according to this formula here, that's going to be the square root of u1 squared plus u2, so -1 squared, and plus 3 squared, okay? So you would get 4 plus 1 plus 9. 4 plus 1 plus 9 is 14. So in this case, the magnitude or the norm of u would be square root of 14. Let me just calculate the norm of v real quick. So similarly, the norm of v would be the square root of -4 squared plus 0 squared plus 1 squared. Okay. So that would be square root of 17, okay? So if you were looking for the angle between the two vectors, you could use this formula to calculate the angle between them. Okay, so u dot v should be equal to the norm of u times the norm of v times the cosine of the angle between the two of them. So like cosine of theta itself is -5 over the square root of 14 times the square root of 17. And therefore you could, if you were asked to do so, you could solve for cosine by, or sorry, theta by doing like inverse cosine or arc cosine of this. Okay. And if you were asked to find the angle data, and I think you would probably just leave your answer in this form. So I wouldn't necessarily worry about like pulling out your calculator and working out the kind of decimal number that it would give you for this. You could probably just leave it in this form. I think that would probably be an acceptable answer for that. Okay. And then maybe just like one more quick computation with these two vectors. If you were asked to do something like the norm of like 3u minus 2v. Okay. So for things like this, I would suggest like actually calculating the linear combination 3u minus 2v first. I forgot my arrows. So like 3u minus 2v. If we calculate what this vector is, it looks like you'll get 6 plus 8 is 14. Negative 3 minus 0 is negative 3. 9 minus 2 will be 7. Okay. So then therefore the norm of 3u minus 2v would be the square root of 14 squared plus negative 3 squared plus 7 squared, for instance, okay? And I'll just stop here, but you can like continue simplifying by computing the squares and adding, okay? So any questions about that? I think probably most of you are kind of familiar with these formulas. Okay. So I'll try to do some like more complicated examples about like dot product and things like that. So that's kind of what I'll do next. Okay, and here I just wrote down some properties to start with. Okay. So yeah, I listed a bunch of properties of the dot product just now. So we'll just touch on each of them real quick. So I already talked about this first property, although I wrote it as like the norm of a vector is the square root of the vector dot product with itself. So this is one of the formulas I wrote down in the previous page. So this is kind of just a restatement of that formula, except I squared both sides, so I wrote it like this. Okay. The second property, basically the dot product, you can distribute. So u plus v dot w, it's u dot w plus v dot w, okay? Likewise here, you can distribute. So this is a u dot v plus u dot w. Okay. When scalar multiplication is also involved, so here let's see u dot product with v. You can pull the scalar like out to the front, if you will, and do like u dot v and then multiply by c. Same if you have the c multiplying the vector v instead. You can pull the scalar kind of outside. Okay. Last property, I guess it's worth mentioning that u dot v is the same as v dot u. So if you just like think about like the formula for the dot product real quick here, it's pretty clear that if you were to like interchange u and v, you would still get the same answer in the end. Okay, so u dot v is the same as v dot u. Okay. So yeah, I wanted to do some examples that kind of involve these properties. So let me start with this example here. So let's say we're given the following pieces of information. Let me see here. So we're given that the norm of u minus 2v. So we're given that this is equal to 7. We're also given that the norm of u is 3. And then lastly, we're given that the norm of v is equal to 5. Okay. All right. And so we're not given the vectors u and v themselves. We just have this information about the two vectors. And then the question is going to ask us to find the cosine of the angle between the two vectors. Okay. Okay. So in order to find the cosine of the angle between the two vectors, we know that we had this formula from before. Okay. And we're already given the norm of u and the norm of v. So to find the cosine of theta, we would also need to know what the dot product of u and v is. Okay. Because we know these two, so we just need to know the dot product now, and then we could solve for cosine theta. So the question is going to be, how can we solve for the dot product, or how can we calculate it, if you will, with the information that's given? Okay. So I'll just kind of spark it out so you guys will see how that works. So we have this information. And what I'm going to do with this information that we have here is, I think I'm going to maybe, I'll square both sides of this equation real quick. So we could say 7 squared 49 is equal to the norm of u minus 2v squared. Okay. All right, so then why did I do that? So the idea here is we want to exploit this first property that allows us to think of like the norm squared as being like a dot product of the vector with itself. Now in this case, though, we have like the norm of u minus 2v squared. So the norm of u minus 2v squared would be like u minus 2v dot product with itself. So I'm going to write it as that u minus 2v dot product with itself now. Okay. So it's like taking the first property and just replacing v with u minus 2v everywhere. It's basically what we're doing. Okay. Right. Okay, so then what can we do with this expression? So the second property that we had here, that the dot product is distributive. Okay. The distributive property allows us to FOIL out expressions of this form. So the next thing that I'll do here is I'm going to like sort of FOIL this out. So we will maybe do like u dot u we have like next u dot minus 2v, which by the third property we can write as minus 2u dot b. So that was u with the minus 2b. Likewise, when we take the minus 2v and distribute it, so minus 2v dot u so it's just 2 and then times b dot u. And then for the last one where we multiply these out, whoops. Okay. So minus 2b dot minus 2b. So we can make that positive 4. And then v dot v. Okay. Okay, so I FOILed this expression out, and then here, let's see what do we have here. So u dot u, remember that's the norm of u squared. Okay. u dot v and v dot u are the same. So let me combine these as like minus 4 u dot v. Okay, because again, u dot v, v dot u are the same, so you can combine them like that. And then at the end, again, this v dot product with itself, that's the norm of v squared. Okay. Yeah, so at the end of the review, I'll stop the recording and then I will upload the recording to our YouTube channel, okay? So I'll maybe do that later tonight. At the latest, I would get it done early tomorrow morning. Okay. All right, let's see here. So we have this, and then we can plug in some numbers at this point. So, okay, so we still have that all of this is equal to 49. So just so we don't like forget it, I'm gonna carry that 49 down to here. Now we know the norm of u was 3, so this is like 3 squared. We have minus 4 u dot v, and then this is a 4 times, and the norm of v was 5, so that's 5 squared. Okay. Okay, so then 49 is 9 minus 4 times u dot v. And then this is 25 times 4, so that's 100. Okay. And what we can do in this equation then is we can actually solve for the dot product. Okay. So I'm going to minus the 9 over. So that becomes 40. Minus the 100 over. So 40 minus 100 is negative 60. Okay. So divide both sides by negative 4. That gets us u dot v is equal to positive 15. Oh, that's very interesting. Okay. So with u dot v being equal to positive 15, the question was ultimately looking for cosine of data. So the idea was we had this equation that we could use to solve for cosine data, but we needed to know the dot product first in order to use it. Now we know what the dot product is, so u dot v was 15. The norm of u is 3. The norm of v is 5 times cosine data. So this is pretty remarkable. 15 is 15 cosine data, so actually cosine data is equal to 1. Okay. All right, so then that would be like the solution to that problem. Okay. The question asks to find cosine data, so you don't need to solve for data itself. Just cosine data equals 1 is good enough. Just maybe as a small aside though, if cosine of data equals 1, if you guys know your unit circle well, cosine is going to be 1 when the angle is 0 degrees or 0 radians. So that's sort of as an aside, we actually can solve for data as being 0. Okay. All right, so any questions about that? Okay, all right. I think this is probably good enough for now. Like I could do some other examples, but I'm wondering if I should move on. I think I'll move on, and maybe at the end we feel like it, and if there's time, can maybe do like another example here. But I think I'll move on for the moment. I guess maybe what I would highlight those, keeping in mind how you can do like a norm squared as a vector dot product with itself, and then being aware that when you have an expression like this, that you can FOIL it out. Okay, I think those are kind of the important things that I would highlight in this example. Okay. Let's see here. So I also wanted to talk about the maximum and minimum values of u dot v, as well as the norm of u plus v. I kind of wrote out a lot of stuff, but as I was writing it out, I was not sure if it would be good for me to actually go over all of it during the review. So when I upload the recording of this review to our YouTube channel, I plan to include like a link to my OneNote, so you'll be able to see like the notes that I've written for everything, in addition to like having the recording available. So I think I will not cover everything that I've written here, just because as I was writing it out and thinking about explaining all of it, I felt like it was a bit too much for the review. But you'll have access to like my notes, so you'll be able to see it. So maybe I'll just kind of mention a couple of things about this topic. I'll mention it kind of off to the side. So just kind of ignore what I have written in black right now. You can take a look at it later. Gosh, okay. So I'm just gonna kind of go over here. So there's kind of two things I wanted to highlight, and then maybe I'll try to do a quick example, and then we'll move on. So we saw earlier that there was this formula relating the dot product and the norm and the angle between the two vectors. Okay. And this equation gives us a couple of interesting things. Oh gosh, well, there's a couple of things I would like to mention, but I'll just focus on what I wanted to talk about first. So we know that cosine data is bounded between -1 and +1, okay? So these are like the maximum and the minimum values of cosine data. The maximum 1 occurs when data is 0, so like 0 degrees or 0 radians. Likewise, cosine will be -1 when the angle data is 180 degrees, or in radians equal to pi, okay? Okay, so that means that when data is equal to 0, so that would be when the two vectors are collinear. Because in this situation, that's when the angle between them is 0. I guess they usually do radians in math, so I should leave it in radians. Okay, so when data is 0, cosine of data is 1. So you get that like u dot v would be equal to the magnitude of u times the magnitude of v. And then this would be like the maximum possible value of the dot product. Okay. Because otherwise cosine data will be smaller than 1, so the dot product would be smaller. And then likewise, when data is pi radians, So the vectors would be pointing in an opposite direction, and if that's the case, because that's when the angle would be 180 degrees or pi radians. So this is when the dot product achieves its minimal or smallest value. And smallest value would be negative norm of u times norm of v. Because cosine data being -1 will give you the minimal value. Okay. So that's kind of like the max and min value of the dot product. I also mentioned real quick the max and min values of the norm, just real quick. So I don't plan on spending too much time during my review talking about it, but you guys probably remember the triangle inequality. That the norm of u plus v is always less than or equal to the norm of u plus the norm of v. Okay. So it turns out that when the vectors are collinear, okay, so when the angle between them is 0, I'm not going to prove it, but I'm just going to state the results. You can maybe kind of see in the picture though. So when they're collinear like this, the norm of u plus v will be equal to the norm of u plus the norm of v. So this would be like the maximum possible value of the norm of the sum u plus v. So the maximum is achieved specifically when the angle between your two vectors is 0. So when they're collinear like this, or parallel, I guess, to be more precise. And then when they are like facing opposite direction, so the angle between them is pi. Okay. That's when the norm of u plus v achieves its minimal value. The minimal value is going to be the absolute value of norm u minus norm v. So that's like the minimal possible value. Okay. And then this was like the smallest or the minimum value of the dot product. So then just like a super like quick example, just to see how these will come into play. So if you just had a question where you were like given that the norm of u is 3, the norm of v is like 7, okay? And then you are asked like what are the maximum and minimum possible values of the dot product? And then like likewise, let's say you were also asked what were just given that two vectors have these magnitudes, what are the maximum and minimum possible values for their norm of the sum? Okay. So in this case, the max possible value of the dot product would be norm of u times norm of v. So 21 would be the largest possible value that the dot product could be. And the dot product would be equal to 21 specifically if the two vectors were pointing in the same direction. The minimum value, minimum possible value of the dot product is the opposite of this. Okay, so just negative 3 times 7, so negative 21 is the minimal possible value. Don't know why I wrote that there. Okay. And then just also real quick, so the maximum value of the norm of u plus b. So just with the information given, the largest possible value of the norm of u plus b would be 3 plus 7. So the norm of u plus the norm of b, that's the largest possible value for it. So that would be 10. And then as for like the minimum possible value with the information that we were given, minimum possible value of the norm of u plus b would be, so I guess using this kind of formula here, the absolute value of the norm of u minus the norm of v. So absolute value of negative 4. So the positive 4 would be the smallest possible value of this norm, okay? All right, so any questions about that? Okay, all right. So then with the time remaining, I guess I just wanted to spend the rest of the review just trying to talk more about elimination, solving systems of equations. We've done some examples that involved doing elimination already, but I just thought I would do a couple more. So let's see here. So right now I have this system of equations, and I might do a couple of things with this example, but the first thing I wanted to do was just solve it using elimination, okay? So elimination plus the back substitution after that, okay? So you guys will be doing this pretty much for the rest of the semester in this class. So even if you don't necessarily like nail down the process of elimination, doing row operations for this first exam, you'll still need to know it for pretty much the whole semester. So with this example here, so when you're doing elimination, you want to start, you want to do it like one column at a time. So start with the first column. This one in the first entry would be like our pivot. And then we're going to use this pivot to eliminate everything underneath it. So to eliminate the negative 2, we could take row 2 and we could add 2 of row 1. And if we want to eliminate this 3, we could also take row 3 and we could subtract 3 of row 1, okay? Okay, so we should have zeros here. Let me check what else we will get. So 3 plus 0 is 3. 1 plus 4 is 5. Negative 7 plus 4 is negative 3. Okay. And then row 3 minus 3, row 1, 4 minus 0 is 4. Negative 2 minus 3 It's -5 and 2. It's going to be +21. Oh, sorry, I'm looking at row 2. That's my bad. I'm supposed to, sorry. So row 3 minus 3 of row 1. So 4 minus 3 times 0 is 4. -2 minus 3 times 2. So -2 minus 6 is -8. And then here we're going to do 2 minus 6, so -4. Okay. All right. So now we've kind of finished the elimination in the first column. So like this one was like the first pivot. So now this 3 is going to be the next pivot. So we want to use the 3 to eliminate the 4 underneath it. So if you're in a situation like this where the numbers are not super nice, don't be like shy or afraid of using fractions if they are necessary. So here, if you wanted to use the 3 as a pivot to eliminate the 4, you would have to take, let's see here, row 3, and we would need to multiply row 2 by 4 over 3 and minus like that, okay? So the way I think about it is I divide by 3 to make it a 1, and then I multiply by 4 to get a 4, and then 4 minus 4 eliminates that guy for me, okay? Okay, so let's see what that's going to leave us with. Okay, so we should have a 0 there now, and then let me write this out. So we're doing -8 minus 4/3 times 5, okay? So that's going to be -24 over 3 minus 20 over 3. So this is -44 over 3, okay? And then just real quick doing the last one. So row 3, so -4 minus 4/3 times row 2, and we have -3 in row 2, so -3. So in this case, the 3's will cancel, so that's like -4. Oh, +4. Oh, okay, that's pretty nice. So that's a 0. Cool. All right. Okay, so then we finished the elimination. So I guess these would have been the pivots that we had. We're not really going to do any more row operations, but if we were to do more operations, we would use this as the next pivot and maybe do some more elimination. But for elimination, you just stop once you go to this upper triangular form. And then we want to do back substitution. So for back substitution, remember that you convert this into a system of equations. So the first row gives us like x plus 2z equals 2. Second row gives us like a 3y plus 5z is -3. The third row gives us a -44 over 3z equals 0. Okay. So then you can solve the last equation, z is 0. Okay. Substitute back into the second equation. So z is 0, you get 3y is -3. So that y is going to be -1. And then lastly, plugging in z is 0. And if there were like a y term, you would also plug in -1 for y. But just plugging in z is 0, and that gives us x equals 2. So then right now, this would have been the solution to the system of equations, okay? All right. So I might come back to this example and do a little bit more work, but before I do that, I wanted to look at some other examples. Let's see here. I have an example here prepared. Let me think if I want to do this one though, because I'm looking at how much time I have left. So I'm just kind of thinking, what all do I want to cover? Okay. I think maybe instead of this, I will do this real quick. Just to sort of touch on something that I talked a little bit about earlier, but didn't quite go in depth on. So same instructions. So for this example, let's say that we wanted to solve it again using like the usual like elimination stuff. Okay. Okay. So this one's so you're not going to get a unique solution this time. So I kind of wanted to revisit what happens if you don't get a unique solution. Okay. All right, so again, here is our first pivot. Want to eliminate this -2 underneath it. So we'll do row 2 plus 2 row 1 real quick. So we're not altering these rows yet, so I'm just going to leave them as they are. So we're doing row 2 plus 2 row 1. So here we got -5 plus 4 is -1. -1 plus 0 is -1, and 2 minus 2 gives me 0. Okay. So then if this is the next pivot, the -1 there, so I'll eliminate the 3 underneath it. Can do that by taking row 3, and we would add 3 of row 2 to eliminate that 3. Now when we do row 3 plus 3 of row 1, you're going to get 3 minus 3 is 0. 3 minus 3, so 0 again. And then we have a 0 plus 0, so 0. Okay. So this is in the sort of upper triangular form now. Okay. So if I were to rewrite the corresponding system of equations, so the first row gives us like 1x plus 2y equals -1. The second row gives me -y plus z is 0. Okay. The third row just basically gives us a 0 equals 0. So there's not really much point in writing it out. Okay. So what's happening in this problem right now is we're actually getting infinitely many solutions. So again, I think you guys don't do too much with infinitely many solutions until like after the first exam. But maybe, I'm not too sure on this, but like maybe you still kind of need to know how to handle this situation just in case it comes up like in one of your problems, right? Uh, so, you know, I'll just ask a general question. What would you guys do when you get to this point? You know, how would you proceed? Anyone know? Okay, so people will do slightly different things at this point, although they're all kind of like the same in the end, okay? I just kind of wanted to touch on like real quick, if you had to like, write out what the solutions are gonna be. Here's how I do it, okay? Even if you don't need to know this for the first exam, uh, you'll be doing this a lot in the future, so I guess it wouldn't hurt to just go over it now. Okay, so here we kind of ended up with only two equations, right? So the way that I think about it is since we have two equations here, that means we're only going to be able to solve for two of our three variables, okay? So we're gonna use these equations to solve for two of them right now. There's a convention that can be very useful to follow in this class, although it's not necessary that you follow this convention. But the convention is to solve for the variables that correspond to the pivot locations in your final matrix. So maybe I'll word it as solve for the pivot variables. This would be how I'll word it. Okay. So each column was representing the coefficients of the variables x, y, and z. So here my pivot variables would refer to x and y, since it was the first and the second column with the pivots here. Okay, so the pivot variables refer to x and y. So z, the variable that's like missing a pivot, these non-pivot variables are what we call free variables. So in this case, z would be the only free variable in this problem. And like I said, everyone will do this slightly different ways, but the way that I kind of do it is this. So since z is a free variable, that means that z is like free to be like any value. And to sort of reflect that z can be any value, I'm going to assign to z like another variable. We call it a parameter. So I'm just going to set z equal to some variable t. T can be anything, so that's what makes z a free variable. Now from there, I want to sort of like substitute this into the equations for z. So we're kind of doing back substitution, if you will. So substitute for z. Here we're going to get y must be equal to t. And then if we sub this into the first equation, we're going to get x must be -1 minus 2t, okay? So then t can be any real number. So the idea is you get one solution for each possible value of t. So therefore, there's infinitely many solutions since there are infinitely many possible values for t, okay? So I guess the idea of this was like z being a free variable, you just set it equal to t, and then these equations will force a value for x and y once you know what z is. So once we know z is t, y is forced to be t, x is forced to be -1 minus 2t. So in that sense, x and y are kind of like not free because they depend on the value of z, okay? So this is kind of how, if you have infinitely many solutions, if you have to like somehow write out what your solutions are and what they look like, people tend to write it in a form similar to this here. Okay. So I'll highlight, so one of the main things I really want to highlight here though is how would you maybe recognize that you have infinitely many solutions when you are doing your like row operations, okay? So there's a sort of a common misconception that I always get from students. And I thought it would be nice if I cleared up this misconception right now. So many students will say that this will have infinitely many solutions because they see this row of zeros. Okay. So I'll kind of caution you guys against thinking that way though. So getting a row of zeros like this, that in and of itself is actually not what leads to infinitely many solutions. So generally speaking, that is not the case actually. Maybe somewhat by coincidence, it's maybe always been the case so far in the problems that you've seen. So maybe that's where the misconception comes from. But what really tells us that we have infinitely many solutions is actually the presence of a free variable, because it's having a free variable that leads to getting the infinitely many solutions, since that variable is free to be any value. Okay. Let's maybe change color real quick. So it's really the presence of having free variables. That is what actually tells us that we're going to have infinitely many solutions. Okay. And specifically, this sort of convention that we followed, that the free variables, if we always choose them from the non-pivot variables, then essentially you'll know you have a free variable whenever there is a column that's missing a pivot. Okay. Okay. So if you have a column without a pivot, that means you'll have a non-pivot variable. So then you'll have these free variables, and therefore you have infinitely many solutions. So the big thing then is if you end up with a column that's missing a pivot, it's that tells you that you have infinitely many solutions, not a row of zeros. Okay. Now, if you have a square coefficient matrix, then to have a column missing a pivot, you'd have to have a row of zeros. I think that's where the misconception comes from. But if you have a matrix that's not square, it's possible to like not have a row of zeros, but to still have a column without pivots and therefore still have infinitely many solutions. So that's just something I wanted to try to clarify right now. I don't remember if you guys need to know how to do this kind of stuff for the first exam. So just in case I went over it, and you'll definitely need to know it in the future for this class. So I guess it doesn't hurt too much to go over it now. Okay. So maybe before I continue, I'll just stop again and ask if you guys have any questions about anything. So it's almost 7 o'clock. I might go a little bit over 7, I'm not sure. There's definitely a lot more things I could talk about. Um, so I usually am not able to cover everything, in a 2-hour exam review. So maybe I'll just leave it with maybe this last example, and think I'll call it a day. So here, I'm just going to work through this final example. We'll end the exam review with that. Again, I'll have a recording up later on YouTube for everyone. I'll share the link to my OneNote so you can kind of see the notes that I have, and any other additional resources I may have to help you guys study for the exam. I'll also share with everyone once I share the recording. Okay. All right. So let's just end it with this review, or this example, and that'll be that. All right. So here it's I think there's a question like this on your homework, if I remember correctly. I think it's a kind of a good type of problem, somewhat challenging. So let's find the values of k, if any, for which this system of equations will have a unique solution, infinitely many solutions, or no solution. And taking a look at the system of equations, you'll notice that k appears as a coefficient in a couple places, and it also appears on the right-hand side. So let's talk about how to go about solving these types of questions. Basically, you want to start by doing elimination. So I'll create the augmented matrix for the system of equations. So k, being a coefficient of some of the variables, is going to appear within the augmented matrix like that. And it's also on the right-hand side, so we also have a k over here as well. Okay. So don't worry too much about the k's, just do elimination. Okay. So like here we have a pivot. We want to eliminate everything underneath it. So I'll start by doing row 2 minus row 1 and row 3 plus row 1. That will get rid of these guys in the first column. Okay. Now here we're also going to get, when we do row 2 minus row 1, we'll get k minus 1. We'll get 3 minus 1 is 2. 1 minus 0 is 1. Here we'll also get row 3 plus row 1. Oh, okay. Negative 1 plus 1, another 0. That's very convenient. And then k plus 1 here. And then I guess this is about k plus 0, so just k. Okay. So you might have to do a couple more row operations, but I guess fortunately here for me, this is already in upper triangular form, so that's very convenient. Okay. Let's use, okay. Now, what I would recommend, once you kind of reduce to the upper triangular form, pay attention to the values of k that will give you a 0 in a sort of pivot position, okay? So for those values of k, you may be getting no solution or infinitely many solutions, so pay attention to those values of k. So in this case, here we kind of have a k minus 1 as a second pivot, but if k were equal to 1, we would actually have a 0 here. Okay. So we'd have a 0 in this like a pivot position, if you will. Likewise, over here in this position, if k is -1, we would have a 0 in that entry, which tells me that something kind of bad or unusual maybe is going on. So I want to focus on these two values of k right now and just see what's going on. So let me start with what's going on when k is -1. So here's what the matrix looks like when k is -1. So I'm just going to plug in -1 for k. So this would be -2 here. And then, like I was saying, you have this 0 in this third position. So now you're like missing a pivot, if you will. And then k is -1, so you have -1 on this side. Okay. So in this case, that last row is telling us 0x plus 0y plus 0z must equal -1. So clearly this is a situation where you have no solution then, okay? Generally speaking, anytime you have no solution, when you do your elimination, you'll get something of the form 0 equals something non-zero, like this here. So that's like the clear sign that you have no solution. Okay, let's take a look and see what's going on when k is equal to 1 as well. So when k is equal to 1, we're also going to be missing a pivot. Okay, so here, when k equals 1, so now that's a 0, so we're missing a pivot. Now down here, if k is 1, you have 2 and 1 remaining here. Okay. So then, in this case, you again only have 2 pivots. So a pivot here, and then I guess the next pivot would actually be this 2, since you don't have anything over here. Okay. It's maybe not a big deal really, but you could quickly, well, no, it's not a big deal. So I'll stop here and, well, I mean, it doesn't matter. It'll be super quick. So if you really wanted to, you could again eliminate everything underneath your pivot, because that's usually what we do with elimination. So I'll just do it real quick, although it's not entirely necessary to do so, but I figure we may as well. Yeah, so if you want to eliminate everything underneath your pivots, you do that. Okay. So this time we don't have 0 equals something non-zero. So it's not no solution, but we do have the case where one of our columns is missing a pivot. So then, as I was saying earlier, a column without a pivot, that is what tells you that you have infinitely many solutions. Okay. Okay, so therefore, we now figured out when does the system have no solution, when does it have infinitely many solutions. For any other value of k, you'll have a full set of 3 pivots. So if you have a full set of pivots like that, you're going to get a unique solution then. So like otherwise there will be a unique solution. So then to answer this question, there was no solution when k is -1. And then we have infinitely many, sorry about that. Infinitely many solutions when k was equal to +1 is what we found here. And then for any other value of k, like I was saying, you get a full set of pivots in this square matrix. That guarantees that you'll have a unique solution. So maybe you could say there's a unique solution when k is anything other than ±1, okay? Okay, so I think that's pretty much it. Any last questions? If not, I'll go ahead and end the review there. Again, I didn't quite necessarily cover everything that was on the first exam. I didn't talk about like elementary matrices, matrix multiplication, things like that. So there's some topics I didn't get to. So be aware of that so that when you're studying, you're not just relying solely on my review, okay?